Okay, I have constructed a makeshift sunshade, although it may come crashing down on me as it's not extremely stable. So anyway, let's see if we can work this example here. Hopefully my sunshade doesn't come crashing down. You would laugh if you could see what I've laid up here. Anyway, but at least the sunspots are gone for the moment. We've got an example here. We've got saturated R134A vapor enters an adiabatic compressor. The minimum power input to the compressor is to be determined. Also determine the exit pressure. And they've given us some information here. So again, we've got a compressor. Right? Draw it kind of in any orientation you like. I'm going to draw it this way, where the inlet is kind of at the larger end and the outlet is kind of here at the narrow end. And a compressor is just a device for our purposes that requires a power input. Got mass and mass crossing the boundary. Okay? Things that we know. Well, we've got an inlet pressure. We've got an exit pressure. 160 kilopascals at the inlet, 900 kilopascals at the exit. We have an inlet volumetric flow rate of 2 cubic meters every minute. Now, it would be different at the outlet because we're dealing with vapor here. It's going to get compressed. So it's coming in at one volumetric flow rate. It's going to go out at a completely different one. We also know it's coming in saturated vapor, saturated R134 vapor, so it's R134A. Let's write that down. And it's coming in as a saturated vapor. Okay. Now, those are the numbers. There's some other things that are given to us here that are not numbers. What might those be? Well, look at your adjectives here. They're using this. Of course, we should know this one. Adiabatic means that there's no heat transfer, correct? Okay. And I've told us something else there that's really important. We just talked about this idea of minimums. They've told us that I'm looking for the minimum power input. And if we think about what is the purpose of this device, well, the compressor, again, the goal of a compressor is to consume power. We provide a work input. And basically using this work to increase the energy of the flow stream. So the minimum power tells me this thing's not generating entropy. It's the reversible device, the best possible version of this device. That's going to be important here in a little bit. All right. Well, it wants to know, it wants to find this power input, this minimum power input. It wants to know the power input. How do we find an unknown power or energy quantity? Well, first law. That's hopefully kind of a gag reflex at this point. So if we do a first law analysis here and we say, well, what crosses the boundary? That's how we do a first law analysis. We say, well, you draw your system we already have here. I've got power in, that's positive. I also have the mass coming in, E dot mass in, and then I'm going out, I've got E dot mass out. And I think we can assume what we call steady flow. Some texts would call that steady state. We like to call that steady flow, meaning the change for the system with respect to time, the dE dt there, is just simply 0. So in minus out equals change. Add the in, subtract the out, that equals the change. It's steady flow, the change is 0. Okay. We say, well, we're after this power input. The energy of the mass in and mass out, I've got a single inlet. This is a chapter 5 problem, right? This should go pretty fast. This is m dot, let's call the outlet 2 and the inlet 1. I did not include kinetic energy because I don't know the areas. They didn't give me the speeds. They did give me a volumetric flow rate. So if I knew the area at the inlet, I could find the inlet speed, and maybe I could find the outlet speed, but I don't have any of that information. So I'm going to have to assume, right, I'm also going to assume that V1 is is approximately equal to V2, the change in kinetic energy is going to be essentially negligible. Okay. So now I've just got to try to quantify these unknowns. So I'm looking for this guy. I don't know the mass flow rate, but I do know the volumetric flow rate. So I can use that. I can use the conservation of mass principle to figure that out. Right? So if I take the inlet specific volume, take the inlet volumetric flow rate divided by the inlet specific volume, that's going to give me m dot. And again, I've got to make sure it's, because this is the inlet volumetric flow rate, I've got to be sure and use specific volume at the inlet. So I can find m dot, assuming I can find this. Well, I need to be able to find H1 and H2, right? So let's assume maybe I can find those. Let's talk about how would I find those. And if I can find H1, I can find V1, so that's okay. And I think we can do that. I think the first one's not too bad. I think I can set this aside now. So I think finding the first one's not too bad. Let's go find now properties. And also, I forgot to write here, we're looking for the power input, but we're also looking for the temperature. I guess it says the temperature at the exit is what the original problem statement says. So we want to know T2. So another thing to find. Okay. So let's go figure out, can we find these properties? Well, we know at the inlet, they've given us a pressure. Right? So go back and look at our givens here. We know the inlet pressure of 160 kilopascals. We know our substance is R134A, and they told us it enters as a saturated vapor. So I'm just going to write X is equal to 1, X meaning it's saturated, 100% in the vapor phase. So that's not too bad. We should be able to find H1 and V1. Just look up saturated vapor properties. Assuming I've got a row for 160, I'm set. Okay, so assuming I can find these, let's, I also need H2 here, right? So let's say, what do we know about state 2? Well, I know the pressure. Yeesh. I don't know a second property. I need two properties. Now the common mistake, the rookie mistake here is to say, oh, well, Steve, it's saturated vapor at the exit. No, it's not. There's absolutely nothing here in the problem statement, absolutely nothing there tells you it's saturated vapor at the exit. It enters as a saturated vapor. You add energy to it, it's probably not going to be a saturated vapor at the exit. Absolutely nothing there tells me it's saturated vapor at the exit. There's no other given information about the exit. We don't know a second property to find because we need H2, right? Okay. Well, let's see here. What else do we know? Is there another law or rule or equation that might get us some information about the second state? Well, we just talked about this fancy new tool called the second law, and this is a rate form. So I'll tell you what, let's do per unit mass. Let's say little s2 if we look at the second law. All right, let's say per unit mass. So the second law, let me give myself just a little more room here. Little s2 minus little s1 is equal to the integral of del little q over t plus little s gen. Okay, what do we know about this stuff? Well, what do we know about heat transfer here? It's adiabatic. So an integral is just a summation of little tiny things. You're going to add up all the differential size slices of heat transfer. If you add up a whole bunch of little tiny zeros, you still get 0. We also know this thing is reversible. How do we know that? Because the problem asked for the minimum power input. The goal of a compressor is to put power in. We want to know what is the device that consumes the least work. What is the lowest power input? So this is 0. That tells me then that S2 is equal to S1, or delta S is equal to 0. That becomes my second property. So let's go back now and get properties. So now we can actually go get properties. We could have gotten some properties earlier, right? There's nothing wrong with this up here. You can add to it if you like. I'm just suggesting maybe we write the second law first and say, hey, do we have everything we need? H1, V1, and now I know I also need to get S1 because S1 becomes my property, my second property at the output. So given these two properties, I think all I need now is just H2, right? That's the only property I need there at the exit. Okay. So I'm looking through, I'm going to assume that you can go to the table and get some of these properties here. And I want to see if they'll pull up on my tablet. Yeah, here we go. Okay, so I've just pulled these properties there, so you can pull those out. You can write those. See if those. Make sure. We've got to be able to find that one quickly, right? So if this were a test problem, right? Look at our equations here. So if this were a test, for me, if this was a 25-point test problem. Probably 5 points here, probably 4 points here, 6 points for showing me you understand why S2 is equal to S1. So 15 points for the fundamental equations involved out of 25 for the problem. Probably 2 points for getting these properties, 3 points for this one because we're going to have to interpolate this one. So, how do we know that? Well, you can see the properties there for saturated vapor, and let's go look. Then let me pull my table up and let's talk about how we get that second properties, H2 and T2. So here's what we know. We know S1. We've got all these. I'm not going to write them down, but I am going to write this one down. 9419. Kilojoule per kilogram Kelvin. Okay. So about 0.94 kilojoules per kilogram Kelvin. We know that. We also know 900 kilograms. We know these are my two properties. 0.9419 kilojoules per kilogram Kelvin. Okay. 900 kilopascals. So we go look, and I'm going to look. I'm going to go ahead and show you the saturated vapor, superheated R134A vapor table here. And so we know our pressure is 900 kilopascals, or 0.9 megapascals. And we don't know our temperature, but here's what we know. We know our entropy is 0.94 something, right? 9419. So that tells me it's between these two. So that means our H value is going to be between these two. And our temperature value is going to be between these two. So we're going to be between 40 and 50 degrees Celsius. We're going to be around 280 for our H value because we're somewhere in between these two. For S value. So you can set up interpolation. I've got a row for 40 and 50 degrees Celsius. H2 minus H at 40 divided by H at 50 minus H at 40. Same thing for T2, because the problem also asks for T2. So T2 minus 40 divided by 50 minus 40, those are degrees C. And what we know is we know the S value. Right? We know S2, that's known. We can go look up the S at 40 degrees, and we can go look up the S at 50 degrees. And we'll come back with the value. Loud pop here.